Please join me in welcoming Simon Eskildsen.
Thank you. Okay, that works. Cool. Yeah, my name is Simon. I'm going to be talking today about two things. I'm going to talk about how all the software that you will build will break, and then we'll talk about how you can build software that thrives in a world where everything will break. This is a great follow-up to Julia's talk, where we're talking about debugging all these problems. And the approach I'm going to take here is that we don't always have the luxury of debugging absolutely everything. And sometimes figuring out the problem is just not going to work. Space is going to emit cosmic rays that are going to change the bits inside of our machine, causing all these things that we can't predict. And we can't always figure out what the root cause is. There is some delicate balance. And now Julia has covered the ground of what you can actually do, and now I'm going to cover the ground on what you're going to do about the unknowns. So yeah, this is something that I have been obsessed with for the past year and a half of how to build this super reliable software. I work at Shopify, and Jen already introduced it. We make commerce easy for everyone, so I'm not going to go over that again. I'm going to put some numbers on a slide here, though. We run over 200K stores. We're running a lot of traffic, and we have a lot of devs who are shipping code constantly every single day. It is my responsibility to make sure that we are up most of the time and that we scale as these shops grow and as we add more shops onto our store. And just shortly about me, here's a big pretentious picture of me in a cardigan trying to trying to look smart and important. I've worked at Shopify on containers. I've worked on running Shopify out of multiple data centers. I've been working on scalability, infrastructure, core Ruby and Rails work, performance, and all kinds of infrastructure work. And about a year and a half ago, I was sitting down with a team and we started working on how can we make Shopify better at responding to failure. As an organization, Shopify is quite good at responding to failure. We let people move around. We put them into learning about things that they don't know anything about. We let them move teams. We hire people into roles that we think they're going to be great at, but they don't know anything about. People are really good at responding to the unknown if they have the right attitude. So as an organization, we did really well. Unfortunately, we hadn't managed to figure out how to do that with engineering. How can we build code that thrives in an environment where things are changing all the time? So we sat down a team about a year and a half ago after the summer of 14, and we were exploring how can we build software that thrives in these environments where things fail, things are unpredictable, and we can't really anticipate what's going to happen. Because at the end of the day, Shopify is not really worth anything if it's not available to our merchants, and the same thing is true for your software. After the summer of 14, we had a series of embarrassing failures that led to us setting down this team that was to explore this idea of thriving on chaos within the software, just like we take pride in as an organization. And since then, this has given us a great peace of mind. This is the best investment we put back into the Shopify application and infrastructure in the past 2 years to increase our reliability and just make everything better about our application and its stability and a better experience to our customers when things do go sideways. I hope that after this talk, you will be convinced that no matter what you do, things are going to fail, and you won't always be able to debug them with the tools that you just learned. I hope that after this talk, every single time you write a line of code, you'll be thinking, what happens if this fails? Is this component that I'm interacting with actually going to do what I think it's going to do? And I hope that I will have equipped you with the vocabulary to go and research this on your own, and we'll talk about some projects to do that at the end of this. So I want to start by a fun example that leads into this. In the end of the 70s, Intel developed this new chip. And this new chip was causing crazy failures. It was skipping instructions, executing instructions that weren't even there in the first place, corrupting data, doing all kinds of crazy things with no patterns whatsoever. Intel got a lot of reports from angry enterprise customers, and there was no pattern to the madness. So they set down a team of researchers to try and figure out what is going on with this chip. And a year later, in 1979, a paper came out from Intel that surprised everyone. The root cause of this was that this chip was produced downstream from an old uranium mine in Colorado, and because of that, the chips were were too radioactive. And when something is radioactive, that boils down to it emitting loaded particles, right? And a chip is basically just all these transistors that have electrical charges. And an electrical charge represents a 0 or 1. If you have a load of particles that comes in, it could change that electrical charge, right? A 0 becomes a 1. Now one instruction becomes another instruction. Some data becomes other data, and things get crazy. And really, your CPUs or the vendor of your CPU goes to a very, very large amount of effort to make sure that it is about 2 to 4 orders of magnitude less radioactive than your shoe. So at the end of really what I'm trying to say here is that we should be building reliable systems from unreliable components. Our overall system should not be relying on everything being reliable. It is naive to think that everything your application will interact with, you'll be able to understand fully. And that's what we're going to explore here. So we'll talk about a couple of different failure layers here. There are a variety of ways that your application can fail. It can fail within itself, which are the bugs that we debug the most often. It can fail when the system is failing. It can fail when the communication layer is failing with other applications. Or as humans, we can fail to respond to these software failures in an appropriate way. And we'll explore all of these layers. So first we'll explore system. I find this one particularly interesting because in a lot of cases, this is not very actionable. If there's a bug in the operating system, you probably won't always have time to dig into it. Sometimes you just have to work around it. Sometimes you do have the time and you will figure out what it is, and it was a great day, but that's just not always the case. When I talk about system, I'm talking about the interactions with the hardware and the abstraction that the operating system provides on top of that hardware. And I'm talking about the failure in the operating system layer, the communication layer with the hardware, or the hardware itself. And in particular, I want to dig into memory here to scare you. Memory is basically just an array of zeros and ones, right? These electrical charges representing different numbers. Now, these bits can change, right? A 1 can flip to a 0, or a 0 can flip to a 1 by changing that electrical charge. Now, this can happen in at least 2 ways. It can happen by some voluntary change, say you change a true to a false, or the other way around in your program. Or something else could cause it. Something else could flip that bit. And that could have serious consequences. Imagine if at any time in your program, a false could be flipped to a true or the other way around. Imagine if it represents a number that dictates how much radioactive therapy a cancer patient is going to get, and suddenly you multiply that with 100 and you've killed them. And there's a variety of things that can cause these involuntary changes to these bits. You can have heat, which we know changes electrical properties of things. You can have radioactivity and cosmic rays, which are these loaded particles, right? Loaded particles that can change electrical charges. It can be due to hardware defects, utilization, electrical problems, and a lot of these are sort of interconnected. Like utilization increases heat, which might exaggerate electrical problems, and so on and so on. Now, cosmic rays don't really happen that often. I think some papers are pretty much in disagreement, somewhere between maybe 30 to 50 times a month on a normal computer. But electrical problems and hardware defects are very common when you have a big fleet. These numbers are from Google, did an extensive analysis on this and published a paper about probably a decade ago or so, and found this scary number on this slide. That's a lot. And this gets even more exaggerated when you go into space, because you no longer have this atmosphere around the Earth to protect you from all these loaded particles that float around space. So this is an example of some kind of space shuttle. And you can see the baseline here is tons of errors per day, like 300 or so flips that are flipped per day that weren't due to the program. And there's this interesting spike here, which they correlated with a solar flare storm, which means that there's an increase in the amount of loaded particles in space flipping these bits. So I want to talk about an interesting consequence of this, which is called bit squatting. And this is relevant to a lot of us because we do web development, and is an example of one of the many security impacts that this has. Imagine that you're visiting the Facebook website. There's tons of these like script loading, image loading, and things like that. Now imagine that we dissect that, we take that domain, the CDN domain where everything from Facebook is stored out of, fbcdn.net, we make that into a bit array, we flip one of the bits, and then we get a new domain, frcdn.net. And then it looks something like this. So I'm going to register that domain, I'm going to set up DNS, I'm going to set up a web server, and I'm going to serve my own script that's going to steal your session, and then I'm going to ruin your life. The author of this paper did this and actually got a surprising amount of traffic by doing these 1-bit error domains off of some of the biggest CDN domains in the world, like Amazon, Facebook, Twitter, and so on. This is real. This happens. And you can go and look at some of the big providers, and you should register those domains because they might be worth a lot. So now I've scared you a bit, and I've exaggerated a picture of memory failing all the time, and that's not quite true. In your laptop, it's pretty true. I checked my own laptop, and it doesn't have any kind of hardware-level protections. Good thing is that a lot of mature applications protect by this themselves. They do checksumming, they store redundant data, you have RAID disks where if one disk fails, you can get the data from another one, you have duplicate data, things like that. The most common thing to do on servers is this very clever mathematical algorithm that I'm not going to try and do justice by explaining, but the idea is that for every, say, 6 bits, you store a couple of bits, and then you can detect whether there were any changes in that bit range. If there were, you can detect them, and sometimes you can correct them completely invisible to the user. And sometimes you can also, and then there are also systems where you can detect them and then just crash the system if you want to make sure that the state is what you expect it to be. So I hope at this point I've convinced you that this is just one of many examples, right? Like we saw the CPU example of hardware failing. We see the memory one. Memory can just start failing. It can fail due to external factors. It can just become bad hardware. Operating system has the same problem. Once you get to a certain scale, things will start failing at the operating system level as well, and you just have to work around it. And the disk has all the same problems as the memory layer. And as your time, as the amount of time that you run an application increases and the amount of scale that you run it at, you multiply these two numbers and you have your surface area for these bugs, right? And as both of these increase, you will start being exposed to more and more and more of this. And a lot of this stuff, you just will not have the luxury of time to try and figure out exactly what happened, so your application just has to deal with it. So let's talk about that. Let's talk about how do we build applications that in the event of these failures that are going to happen, will thrive, or at least be indifferent to. So from reading tons and tons of root cause analysis of from the aviation industry, from the spacecraft industry, of very, very expensive things crashing, the number one thing that I learned that I think is applicable to normal software development is this idea of graceful loose coupling. What I was searching for when I was doing my research was, there are these companies that have way, way higher stakes when they're programming than we do. If they crash, they kill people. That's not, I help fuel American consumerism, and if I don't do that for 5 minutes, it's probably not that much of a big deal. But, so I was looking for that thing that I could identify from the aviation industry or aerospace engineering, from something that they're so good at, which is building reliable software, that I could apply to what I'm doing. What is the lowest hanging fruit? And from compiling all of this stuff, really the common theme is this idea of graceful loose coupling. And you might have heard about loose coupling before, that your interfaces should be loosely coupled. It is software design paradigm, but that's not really what I'm interested in here, although they tie very well together. What I'm interested is in avoiding cascading failures. If you have all of these components and they're tightly coupled, it means that if one of them dies, all of them die along with it. I want to make sure that if this cell over here dies, you can think of it as a human cell. As a human or an animal, if the cell over here dies, all of the other ones are still working, and then over time, the cell over there recovers, or maybe it's replaced by another one. An example of what's not loose coupling is this guy here. This was built by the European Space Agency, and the rocket flew into space, but the rocket part, the first stage, failed to actually detach from the thing. So what happens then is it runs out of fuel, and then it dumps into the ocean somewhere north of Greenland. This is an example of quite literal tight coupling, right? Because the thing is actually coupled to the thing and it couldn't actually detach it, right? It's just bad software, bad testing, and bad everything else. Now, while that's an example of a big fuck up, what usually happens is that it's not just this one error that causes something to fail. I'm sure that was the case in the rocket example from before either. What actually happens is that something fails to respond to that, something else fails to respond to that, and then 50 errors down, your plane crashes and people die. So the good news is that if there are these 50 points, then if we intervene at any one of these points, we're good. We've saved it, right? And there's 50 of them. So while there's an exponential amount of combinations of ways to get to that failure where things crash and people die, there's also an exponential amount of places that we can hook in and make sure that these failures don't happen. And the first and most important thing to do here is to have these redundant backups, and optionally with sort of degraded functionality. Aviation and commercial airliners are a great example of this. They have 2 jet engines. They actually only need one, so if one of them fails, they just keep flying with the other one. And this is a really great example because they're actually both proved to be operational at all times. Another example from that industry would be if the autopilot fails, well, in that case, you can just, the pilot can just take over and do his job or her job. So what they have here is they have a defined primary responsibility and then some kind of secondary behavior. Now, what's different about the secondary behavior is that it's often degraded and optimized for correctness and simplicity rather than features and performance that the primary component might be, right? It's nicer for the pilot that the autopilot works, but if it doesn't, we just go to the simple thing and let a person control the plane. At Shopify, we call these fallbacks, and we define this as sort of a secondary behavior with degraded functionality to counteract some primary functionality of some feature, right? And I'll give an example of what this means in a second. What I'm trying to accomplish with this graceful loose coupling I'm talking about is the idea that we shouldn't be allowing a single component out here, a single cell of this infrastructure, to compromise the availability or the performance of the entire system. This should not be a domino infrastructure. And this ties really well together with what I was saying in the start. We want to build these reliable systems from unreliable components. How do we do that? Well, we make sure that if any component fails, the rest of the infrastructure is fine with it. So we'll look at a more concrete example here. Let's imagine we're selling shoes, and when we're selling these shoes, we're actually requesting different services and different layers to render this page. It has many dependencies. And now we'll imagine that the session storage layer fails. This is the layer that is responsible for allowing people to sign in and register and sign out and functionality like that. So imagine that fails. By default, something like this probably happens in a high-level language. An exception is raised, it doesn't know what to do with it, and some kind of garbage page is showed to the user. But this breaks that principle from before. We've just allowed this single orthogonal component to the overall responsibilities of this application, which is to sell things to people. That's not the same as allowing people to sign in, right? We can still sell things to people even though they're not signed in. So we've broken the principle from before. We've allowed a single dependency to compromise the availability of the entire system. So what we can do instead is we can just sign the user out, right? If the session storage layer is not working, let's just sign people out and just not allow them to sign in, and then we can still have them check out. They can still browse the store. It doesn't really matter that much. We've just made this graceful loose coupling of something that used to be tightly coupled. And by default, things are not loosely coupled. You have to make an effort to actually do this. And in this case, people don't even notice. The customers just browse around. Most of them probably won't even notice that this layer is down. Our infrastructure team will fix it right away. It will probably only take 5 to 10 minutes, then it's back up. But everyone is calm. Everyone knows what's going on. No one is panicking. So the connection here is that the application sort of builds on top of these building blocks of the system and then communication with other applications. And this communication layer is a huge surface area for failures. And the way I like to think about it is that if you have all these cells that interact with each other, all these services that interact with each other, and a single one of them failing will take all the other ones down with it, you now have a much bigger surface area for failures, right? So if this one fails over here or this one fails over here, the entire thing is down. And this means that now your uptime suffers the fate of this microservice equation, as I like to call it, which is that if you have, let's say, 2 hours of downtime for every single one of those services, and you have, let's say, you have n of those services, then your uptime for your entire platform, if everything is tightly coupled, is those 2 hours to the power of how many services you have. That very quickly starts to look like this. You now have exponentials working against your downtime, and hours of downtime for each component, which is very reasonable, turns into weeks of downtime for your entire infrastructure. So now you might be thinking, okay, that's great, but I have no idea how to get this overview. And that's what we were thinking, and we came up with this thing called the Resiliency Matrix, where at the top we sort of graph the high-level business objectives of an application. In Shopify's case, that might be something like the storefront where people are browsing products, checkout where people are actually buying the products, and administration where people are managing their products and things like that. And then on the left, we have all the different services that make this up. This might be a MySQL database, it might be some kind of message buzz, it might be something like a shipping provider or a payment gateway or something like that. And then each cell represents what happens when the component on the left is unavailable. So in this case, you can see something like when the MySQL master is down, the administration is also down. These two are tightly coupled. And maybe they have to be in some cases, but every single one of those red cells determines a single point of failure for your infrastructure. And when we colored this out, we were shocked by two things. One, how red this was, and two, how hard it was to populate this entire matrix. So we built a tool to do that. We built a tool called Proxy, which allows us to simulate these failures and actually write tests around them. So every single one of those cells are actually tested in Shopify. And they look something like this. Every single cell has a test that corresponds to it that says, oh, when this service is down, this is what I expect the application to behave like. And it proves that it won't degrade over time. So this is all great when things just fail, right? When something fails and you just get an error back right away, you can serve the fallback. But that's really the case. Usually failures happen in interesting ways where there's slowness, there's some kind of network partition, there's congestion on the network, something else that we get back as slowness. So the next question we started asking ourselves was, when is something slow enough that we just wanted to assume that it's going to fail? And then we serve it back. If every page load takes 10 seconds, that's a terrible customer experience. And if that's for something like the sign-in, this like very, very orthogonal component to the rest of the business logic of the application, then we might as well just kill that functionality for a bit. And it also looks something like this, right? If you have a 20-second timeout on something that you're communicating with all the time, your response time climbs a lot. And because of that, you can handle less requests. Your throughput goes down. There's this inverse correlation between the two, that when your response time goes up, your throughput goes down because your application just won't be able to cope with as much load. So these are timeouts, right? I'm talking about timeouts. But the problem with timeouts is that they will waste all kinds of resources like the graph before shows, and the response time will be up by at least that much, which might be a terrible customer experience and have all kinds of other implications. So we actually need something better than timeouts because we need to trigger that fallback that we work so hard for more often in the cases and in a better way than timeout. So we need to fail faster in order to have both of those graphs be steady in that case. And there are tons of ways to do this, and the most common one that is thrown around in the past couple of years is this idea called circuit breakers. And the idea is essentially that if you request something a couple of times and it's timing out, let's say 2 times in a row, we will just assume that it's going to fail for the next 30 seconds. After 30 seconds, we request the resource again and ask, hey, can I get this data now? And then it will respond back with a timeout, and then we'll refresh that window for another 30 seconds, right? So it's a really simple idea that allows failing much, much faster than triggering these timeouts all the time, giving a bad user experience. So now we've talked about how we can write software that responds well to failure. Now let's talk a little bit about how we can have humans respond well to software failure. So when I started preparing for this talk, I had a more ambitious idea. I wanted to talk about antifragile software. So antifragility is this idea that's come up in the past couple of years of the antonym, the opposite of fragile, is not something that is robust or solid. Something that is fragile is something that breaks under pressure. Something that is robust is something that is indifferent to pressure. Something that is antifragile is something that gets better when you apply pressure. What if we could build software that is not just indifferent to failures, but actually becomes better because of them? So I explored that. Turns out that's really fucking hard. But it's a great idea, right? So there are a variety of ways of doing that. If you're interested in that, come talk to me afterwards. But it's not practical today. But we can apply this idea to humans, because humans are very, very good at responding to things in an anti-fragile way. We get better from every failure, and a lot better. An example of this would be something like the root cause analysis of a plane crash. When a plane crashes, we're not just trying to prevent something exactly like that plane crash to happen again. That's not ambitious enough, right? If we have these 50 things that failed that caused that plane crash, the probability of those 50 things happening again is very small. But if we can identify these 50 things that failed and set an intervention point at each one of them, then we've exponentially reduced the entire space of different failures, right? Meaning that this single plane crash didn't just prevent the next plane crash, it prevented the next 100, thousands of plane crashes because we added these new things. As a result, the aviation industry has gotten incredibly good, especially because all this information is shared globally, right? When a plane crashes, it's usually a multinational investigation to figure out what happened. Now, how can we do this with software? Well, when software fails, we can sit down and think about, okay, what actually happened, and not just have action items that identify exactly this very, very specific failure, but go one abstraction level down and try to identify the root cause so that we eliminate not the next failure, but the next hundreds of failures. When you get really good at this, you can add this extra layer of process, which Netflix has, which is this idea that if you're really good at dealing with software failures, you should be able to go into your data center, plug off a node, or introduce artificial latency. Or if you're really good, you kill entire data centers and nothing happens. You're fine. Your application responds well. So you're killing servers in production just to get this practice. So now we've talked about a lot of tools to do this. And the way that I want you to think about this is this sort of resiliency maturity pyramid that you're transcending over time. And you're climbing this pyramid with the requirements that your scale demands. If you have a lot of people who depend on you, like Shopify does, then you should probably be in the green area here. If you're just starting out, then you can probably be in the red or lower orange. But there's not really, once you've sort of gotten that initial momentum, everyone should be in this orange region. Everyone should have toxic proxy tests. Everyone should have, or something like it. Everyone should have a resiliency matrix so they know what's going on in their application. And the last thing to sort of round up all this information that I've talked about and mental model that I want to introduce is this idea of balancing reliability with failure tolerance, right? One way to respond to a failure is to try and increase the reliability of that component. How often can we blame it for failure? Well, let's try and make it more reliable. The other one is to be pessimistic about the reliability of every component that you're interacting with, and you have to sort of balance these two, right? Sometimes something needs another 9 of availability. Sometimes you just need your application to be better at responding to failure. And they sort of come in these groups of, you have sort of the foundation at the top right, which are things like operating system, the programming language you're using, ECC memory, aerospace engineering is up here. These things that are really foundational that has to be really, really, really good. We don't want to blame this for failure very often. It has many 9s. Then down here at the bottom left, you have probably your app, probably most apps in the world. In the middle here, you have sort of the maturing apps that are starting to adopt these patterns that are using a lot of these reliable components to the top right. And then you have sort of the maturing apps here. So why I think this is so powerful is that every time you introduce a new dependency into your application, you should be thinking about where does it fall on this 2-dimensional chart, and where is it taking my app? You can think of this as like vector addition math, right? Of like, if you have your app here and you're introducing a component down at the bottom left, then that will take the reliability of your app down and the failure tolerance down, right? That's not a good thing. I think this is a really powerful way of thinking about, and every time you're introducing new dependencies, I think you should think about this graph. So we've talked about a lot of things here, and since you're all students and eager to learn, I put some of the projects that I built to help me explore this field, and I put a bunch of ideas of things to explore. And if you explore some of this, I would love to hear about it. If you have other ideas for things to explore, I would love to hear about it. And if you love working on this, you should come work with me on my team at Shopify. So final remarks here is that you should think about one of your projects and think about where it falls on that maturity pyramid. Place it, and then think about where you should be and how to get there. Just accept that everything will fail and become excited about it, right? Start researching it and build apps that just do really well on the failure. Make it fun. Make the process fun. And then be careful when you're introducing new dependencies. Where do they fall on that 2-dimensional chart and where are they going to take your app? This is compiled by the work of a lot of smart people. We built libraries to do this stuff. We've used a lot of libraries. There's tons of great resources, especially one that I want to endorse is the Release It book, which is absolutely phenomenal on this subject. I've done other talks on the subject. We've written some blog posts with some of the content from here, and some of my coworkers have done the same thing. And if you want to have reference to some of the papers that I've used for this talk, you can come up to me or email me afterwards. Thank you so much.